My name is Ravi Babu, Assistant Professor in Institute of Aeronautical Engineering College. I am going to teach in digital control system. In this topic, I am moving to fourth module, that is stability analysis. Stability analysis. In stability analysis, today's topic is bilinear transformation and Routh stability criteria. Routh stability criteria. In previous section, we see the introduction of the stability, asymptotic stability, bounded input, bounded output stability, internal stability, and jury stability with some problems. And today we are going to see the bilinear transformation and Routh stability test for digital control system. Generally, the bilinear transformation of Routh stability test of a digital and discrete and sample data systems is same. The Routh stability test is applicable to the systems represented using transfer function in S-plane. It is also complex planes. In case of the complex planes also, it will be applicable, having the same stability conditions as that they are applicable to in S-plane. So now I am going to the jet transfer the jet plane into new complex plane. For that one, we are having the follow the steps. That is, the inner part of the unit circle is transferred to the left half of the new complex plane. Left half of the new complex plane. That is, already we know in the S plane we having the it is your plane. In case of the digital control system, if I am taking the, it is a unit circle. It is a unit circle. Inside the unit circle, nothing but it is a stable. Outside the unit circle, nothing but it is a unstable. Within the unit circle, nothing but that is the poles are zeros. Okay. Within the unit circle, on the unit circle, nothing but it is a marginally stable, whereas the poles are zeros are repeated in on the unit circle at one same place, it is called as a unstable. It is called as a unstable. Same. That is, outside of the unit circle and the unit circle repeated poles is also called as a unstable. Already we seen in the introduction part this one. Now, what I am saying is, in case of the Routh stability criteria, okay, we are going to taking the unit circle as transfer into the new complex phase, new complex plane. That is, this one is transferred to this complex plane, this complex plane. Okay, that is, inside the unit circle, I am taking as a left half of the S plane. Left half of the S plane. Okay. That is the your first point. The inner part of the unit circle is transferred to the left half of the S complex plane. Now, the circumferences of the unit circle in jet plane is transferred to the imaginary axis on new complex plane. That is, this is your circumference of the unit circle. Okay, circumference of the unit circle. This is going to be transferred to in S. It is in imaginary axis. Okay, in imaginary axis. In imaginary axis. That is, finally what I am saying is, the circumference of the unit circle is going to be, in case of jet plane, is transferred into the imaginary axis of the new complex plane. New complex plane. Next, the outer part. Generally, the outer part is called as a unstable condition. Okay, unstable condition. That is, the outer part of the unit circle in jet plane is going to be transferred to right half of the S plane. This is outer part, no? This is nothing but it is transferred to right of the S plane. Right half of the plane. Okay, right half of the plane. This is the comparison of bilinear transformation of stability in case of the low stability condition in discrete time systems. This is the new bounded modified RH criteria stability, where here we are going to finding the stability condition by taking the considering the unit circle as the reference, and it is going to be transferring to the new plane. We are taking these are the conditions. Now coming for this one, in case of the jet plane, I am taking the new plane as W plane, transferring that unit circle into W plane. When we are to planing transferring to the W plane will be satisfy the above three conditions, and the bilinear transformation between the jet plane and W plane will be the equation is very important. This one is z of 1 plus omega by 1 minus omega. 1 plus omega by 1 minus omega. That is, in case of the jet plane, this one 1 plus omega by 1 minus omega. Whereas, in case of the double plane, that is, in case of the RH criteria in normal domain, that is in control system, that is W equal to Z minus 1 by Z plus 1. Z minus 1 by Z plus 1. So, finally, we have to substitute these values into your given characteristic equation for finding the stability conditions. Whether after that one, we are going to moving the duty stability condition of table for finding the RH criteria tables. So, for that one, explanation of this RH criteria for modified jet transform, modified RH criteria, I am considering the one example. Remember that Z value is 1 plus omega by 1 minus omega, or omega value is Z minus 1 by Z plus 1. So, when the problem is given, we have to identify it is a new plane or old plane. That is, old plane nothing but unit circle, Z circle, and new plane is nothing but that is transferring to S plane, that is nothing but W plane I am considering here. So, for that one, these are the steps we have to follow for finding the stability condition. That is, first of all, transfer the P of Z equal to 0 to P of omega. That is by similar transformation technique. Just we have to put where Z is there in a problem, in any transfer function, we have to put 1 plus omega by 1 minus omega. This is the first step. After that one, you have to apply the RH stability criteria test for PW of 0. Already we see the in control system, how can you apply the RH criteria stability of the any transfer function, any characteristic equation. Okay, identify the rows and identify the conditions you have to see in orally in control system subject. So, same as possible we have to do for RH criteria in case of the discrete time control system problems. Just we have to first of all replacing the Z value is with 1 plus omega by 1 minus omega for a given transfer, for a given characteristic equation. So, here I am taking the one of the example is, that is, one characteristic equation P of Z equal to Z cube plus 2.1 Z square plus 1.44 Z plus 0.32 equal to 0. So, I am going to finding the, by using bilinear transformation technique and by using the stability test, we have to find out whether the given characteristic equation is stable condition or not? Or not? So, first of all, I am taking the given equation, that is P of Z equal to Z cube plus 2.1 Z square plus 1.44 Z plus 0.32 equal to 0. That is, after that one, already we see that where Z is there, we have to replace with 1 plus omega by 1 minus omega. So, that is Z equal to, we have to replace as Z equal to 1 plus omega by 1 minus omega. So, substitute the Z is the old plane. That was converted into new plane, that is P of omega. P of omega. So, I am taking the new plane for finding the stability condition. For that one, here I am taking the Z value is 1 plus omega by 1 minus omega. Substitute this one value is here, that is 1 plus omega by 1 minus omega whole cube plus 2.1 into 1 plus omega by 1 minus omega whole square plus 1.44 into 1 plus omega by 1 minus omega plus 0.32 equal to 0. Okay. And we have to simplify these equation for getting the one of the characteristic equation in new plane, that is W plane. So, in the equation is taking the LCM of this one, the power is, the highest power is 3. So, 1 minus omega 3 is there. So, 1 plus omega whole cube into, okay, 1 plus omega whole cube plus 2.1 into here 1 plus omega whole square into one term is coming here. Why? Because it is square term, here third term. That's why remaining one term is coming here. 1 minus omega plus 1 plus 44 into this 1 plus omega multiplication factor into here the power is 1, here the power is 3. So, square term is coming here. 1 minus omega square plus 0.32. It is a constant. That's why the total power is coming to here. After taking the LCM, we have to simplify the equation. Simplify the equation. That is, make it equal to 0. Make it is equal to 0. So, what happened? Omega's cube plus, what is the previous one? 1 plus omega whole cube formula. A plus B whole cube formula you have to write down there. That is omega cube plus 2 into omega square plus 3 omega plus 1. 3 omega plus 1. That is A plus B whole cube form. Up to here 1 plus omega whole cube. Up to here 1 plus omega whole cube. After that one, 2.1 into 1 plus omega whole square. That is omega square plus 2 omega plus 1 into 1 minus omega plus 1.44 into 1 plus omega into 1 plus omega into 1 minus omega whole square. 1 minus omega whole square. A minus B whole square. Omega square minus 2 omega minus plus 1 plus 1 plus 1 plus 0.32 into A plus B whole cube. Same form. A plus B whole cube. That is 1 minus 3 omega plus 3 omega square plus omega cube. Plus omega cube. Okay. Sorry. It is minus 1 minus omega square. 1 minus omega whole cube. Okay. This is 1 minus 3 omega plus 3 omega square minus omega cube. Okay. Simplify the equation with orders notation. That is omega cube plus 2 omega square plus 3 omega plus 1 plus 2.1 into multiply this one into in the inside. So what happened? minus omega square minus omega cube and omega minus omega cube minus omega square plus omega plus 1. It is coming. Okay, simplify this one. If you are getting here this one, that is omega square plus 2 omega plus 1 minus omega cube minus 2 omega square minus omega. So what happened? Minus omega cube. Minus omega cube. Next one is 2 omega square, 2 omega square minus omega square. Okay, plus omega plus 1. We got it. Okay, next. Go for the next one. Next one. This one. So, what we have to get? Omega square minus 2 omega plus 1 plus omega cube minus 2 omega square minus 2 omega square plus omega. So, we got it as omega cube minus omega square, okay, minus omega plus 1. So, if you simplify this one, we got the value. This is your value. Omega cube minus omega square minus omega plus 1. Okay, this is your value. Coming for next term, 0.32 this one. After that one, I am going to taking the order wise common. Order wise common. That is, omega cube is common. I am taking. So 1 plus, okay, 1 plus, sorry, omega cube is common. 1 minus, where is the omega cube? 2.1 omega cube here, minus 2.1, minus 2, sorry, yeah, minus 2.1 is here. After that one, omega cube 1.44 here, and after that one, where is omega cube here? Minus 0.32. So it is omega cube completed. Plus omega square 2 and 2.1 minus 2.1 and minus 1.44 omega square term. No? Okay, right. Here minus it is there. Minus 1.44 and omega square term plus 3 into this one. 0.96. 0.96. After that one, omega term. For omega term, 3. In first one, 3. After that one, 2.1. After that one, minus 1.44. Minus 1.44. Okay. After that one, plus 0.32 into, sorry, minus 0.32 into 3. 0.96. 0.96. Plus constant terms. That is 1 and 2.1 and 1.44 and 0.32. 0.32. So, simplifying this one, it is 0, I think. Sorry, it is wrong. It is 0. It is omega cube. Omega cube. 0.02 into omega cube plus 0.42 into omega square plus 2.7 into omega plus 4.86. You got the value this one. Okay. So, this is the bilinear transformation method. Okay. Bilinear transformation method for solving the, in case of the Routh stability criteria, okay, for leisure control system problems. We got this one. So, what we got? 0.02 omega square. I am writing here. Omega square, sorry, omega cube plus 0.42 omega square plus 2.7 omega plus 4.86 equal to 0. 0.02 omega cube. Okay, it is cube. Remember, mistake cube plus 0.42 omega square. 0.42 omega square plus 2.1 omega, 2.1 omega plus 4.86. It is your characteristic equation. What is type of characteristic equation? It is transfer of z plane to omega plane. Z plane to omega plane. It is modified. It is modified. Okay, RH criteria for solving. Okay. In case of the control system, if they given directly transfer function, you take the directly. But here, in case of digital control system, if they given any function, if they given any type of function, you have to first convert it into, that is z plane to omega plane. Okay, z plane to omega plane. So finally, we got the value as this one. Now, after that one, we go for the same conclusion. And as in control system subject, we do the Routh array. Routh array method. Up to here, you not see in control system. Directly from control system, we take the characteristic equation, we find the Routh table, directly we do it. Whereas, in case of digital control system, first of all, convert that one into Z formation into, in case of the omega formation, we have to, first of all, put as Z equal to 1 plus omega by 1 minus omega. That is this one. 1 plus omega by 1 minus omega. After putting this value, Z, after putting this Z value, we are getting as equation is in bilinear transformation equation, that is 0.02 omega cube plus 0.42 omega square plus 2.7 omega plus 4.86. 4.86. So, make the Routh array table. Make the Routh array table. That is, already we know that in case of the control system, the Routh table will be formed with as some properties. Some properties. That is, here you have to taking the Routh table formation. The first two elements are from the modified characteristic equation. Characteristic equation. When you are going to RH criteria, first of all, you have to identify the highest power. Identify the highest power. What is the highest power of the given equation? That is third order characteristic equation. Characteristic equation. It is third order characteristic equation. So, I am writing as third order characteristic equation. So, I am writing the first term here. First term here. So, it is odd number. It is odd number 3. So, the magnitude of this value is 0.02. 0.02. I am writing here first element as 0.02. 0.02. After that one, I am going to taking as, it is third order, no? Third order element. Third order. Now, I am going to, after this one, the next element I am taking as first order. First order element. What is the first order element in a given problem is, that is, it is this one, omega. For this value, the magnitude value is 2.7. I am taking it as a 2.7. 2.7. So, in first row, I am taking the as a highest order term, that is omega 3. That value magnitude is 0.02, and this is the order as odd number. That's why the next number is, the order is first order term, that is 2.7, completed. After that one, we have to mention is below of that one, n minus 1, that is n equal to how much value? N equal to 3-year order, n minus 1 nothing but 2. So omega square. So write the omega square term. That is, it is second row. It is second row. So it is second row, no? That's why here in a problem, Cauchy equation, the second order system is this one. For this one, the magnitude is, this is second order system, second order term. The magnitude of second order term is 0.42. This one, 0.42. After that one, you have go for the zero order term. Okay, zero order term. What is the zero order term? That is 4.82. Okay, this is in case of the RH criteria. That is, from the Cauchy equation, we have to identify the first and second rows. We have to identify the first and second rows only. After that one, we go for the RH criteria rules. What is the RH criteria rules? Already we see in the control system subject. We have to apply here same rules. That is, whereas we have to write one more point is very important is, in previous section we see this one is jury stability. Okay, I am comparing that one. In case of the jury stability, similarly here the first row will be from left hand to right hand. That is 4.86, 2.7, 0.42 and 0.02. This is your first row in case of the jury stability. What is the second row? Reverse of this one. That is 0.02, 0.42, 2.7, 4.86. It is in case of the jury stability. Okay, this is the method. Already we see in previous sections. Whereas in case of the RH criteria, it is in this formation. Now, what is the next term? N minus 2. How much value? 1 order, first order. That is third row. Okay, this is your third row. How can you find this one third row? W1. W1 is you have to find, if you take this is a matrix, that is ABCD matrix. For this one, determine what is the ABCD values here. That is, the ABCD values as 0.02 and 2.7 and 0.42 and 4.86. Okay, the magnitude of this one is AD minus BC. So, if you have to find this one is 0.02 into 4.86, okay, AD minus BC, 2.7 into how much value? 0.42. If you find this value is 2.4686, we got it. That is W1 value. What is the next term? It is not possible. Why? Because the term is going to close here only. So completed. Coming for the next row, that is n minus 3. That is 0. 0 nothing but constant term. Here, constant term is the fourth order. Last term, constant term. That is omega naught. So similarly for this one omega naught also you have to find. So what is the basic reference matrix here? That is 0.42 above values, above 2 rows. For this one, above 2 rows is omega 3, omega 2. For omega 1. For omega naught, above 2 rows is omega square, omega 1. 0.42, 4.86, 2.4686 and 0. Find out this one, AD minus BC. What is the value? So, AD equal to AD equal to 0 minus BC equal to 4.86 into 2.4686 by AD minus BC by, okay, C value, that is 2.4686. Here also, we not mention directly, I have written, you have to make it as by this value 0.42. 0.42. Okay, I not mentioned here. So AD minus BC by which value? That is C value. C value. So if you got it, this one and this one and it is this one and this one is cancelled. Only we got it 0.46. Sorry, 86. 4.86. Sorry, 4.86. We got it 4.86. Okay, 4.86. So it is completed. So all the Routh array tables or values are same. So we have to take the properties of Routh array, same as in control system. So there is no sign changes in the first column. In first column, there is no sign changes. All are positive. All are positive. Sir, you are getting the minus no. So it is magnitude. That is nothing but your magnitude taking. That is 4.86 is positive. Okay. So there is no sign changes. So finally, what I am saying is, it is the system is stable. The system is stable. Okay. So this is a problem for by using RH criteria. RH criteria. Okay. So for a given characteristic equation, by using, in case of the binary transformation of the digital control system, this is the procedure for finding the RH criteria. Okay. So we can see the next class, one more problems on this one topic. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.